So today we have the Lyman-Continuum production efficiency of faint galaxies that Reionize universe. It was Daniel Lam, but Estefana will present
Thank you.
this talk.
Good morning. Sorry for showing up again. So today I will present you some of the work done by Daniel Lam in Leiden, together with Richard Bowens, on the Lyman-Continuum production efficiency at high redshift. So Daniel is finishing his PhD thesis now. He was supposed to give a talk today, but in the end he didn't make it. So reionization is a major phase transition in the history of the universe, during which neutral IgM, neutral hydrogen, was converted into ionized hydrogen, IgM, mostly hydrogen. From observation, we know that most of the hydrogen was already ionized by redshift about 6, and observation together with modeling are suggesting that reionization took place between redshift, let's say, between 15 and 6 or so. So it was a relatively fast process. I think I can safely say that we are converging toward a picture where galaxies were the major sources contributing to reionization, although quasars could have also played a role. And also among galaxies, the brightest one could have also played an important role. This has been shown recently, for example, here, from a larger fraction of Lyman alpha detection among the brightest galaxies at redshift 8, so that we think that these very bright, massive galaxies could have produced very large bubble of ionized hydrogen, which could have helped reionization. But of course, the most likely source of ionizing photons are low mass galaxies which live at the faint end of the UV luminosity function. A couple of days ago, I already shown you some of our results on the faint end of the UV luminosity function. And here, just a bit of introduction. So the rate of ionizing photons depends on how many photons in total are produced by star formation, which is basically measured by the luminosity functions. And out of this, how many of these are able to ionize, have energy sufficient to ionize the hydrogen, which is the ionizing photon production efficiency, usually labeled with psi ion. And out of this, again, how many are able to escape the galaxy. So traditionally, the ionizing efficiency has been estimated from SED models, helped by the measurements of the rest frame UV slope beta. But this, as you can see, can introduce very large systematic uncertainty. So some help comes from the observation of emission lines in the rest frame UV, such as the carbon-4, which are very sensitive to the ionization state. But these measurements, spectroscopic measurements, are very time-consuming, and these were done only on can be done right now only on the brightest sources. So a different approach instead could be that could use another physical fact. So which is that recombination lines, hydrogen recombination lines, directly probe the amount of ionizing radiation. There is a very linear relation between the luminosity of the H-alpha line and the number of ionizing photons. And this was explored at high redshift by Richard Bowens a couple of years ago, between redshift of about 4. And he found out, basically, he was able to measure the Xi ion. But of course, in order to measure H-alpha at current spectroscopical facilities allow us to measures H-alpha only up to redshift of 2. So how can we measure H-alpha at redshift larger than 4? With spectroscopy, of course. But we have to relax by a little bit our requirements on the resolution. And I'm talking about, of course, photometry. So here I'm showing you some diagrams. The blue curve here represent the IRAC 3.6 filter transmission, and the red, the 4.5 transmission. Also labeled are the main emission lines, H-alpha, nitrogen 2, and sulfur. So we see that as we go to higher and higher redshift, H-alpha enters the 3.6 band, goes through the band, and then finally exits, and finally also enters the 4.5 band at a redshift of about 5. And this process can be tracked with, well tracked with photometry, and in particular by measuring the color between 3.6 and 4.5, as I'm showing here, we can have an estimate of the equivalent width of H-alpha and/or other lines. So Daniel took about 100 galaxies from the Muse sample, so that we have accurate spec Z over the Good South region, which also benefits from deep IRAC coverage from the GRADES program. So deep, when I say deep, it means that the depth of the IRAC matches the depth of HST images in the candles HST deep regions. So we have basically a full SED at the same signal to noise. Thanks to this sample, he's able basically to extend by about one magnitude, 1.5 magnitude towards the faint end of the UV luminosity function at redshift around 4. So spec Z are fundamental, are very important for this work, because in this way we are always sure that the 3.6 band will always contain H-alpha and nitrogen 2 and again other minor lines, while the 4.5 band will always contain the sulfur lines. And so when we do stacking, because he did stacking, we are always sure that we are doing things consistently. Stacking was done not on the flux measurements, but on the actual images. But before doing this, we need to clean the cutouts around each object from the neighboring sources, which could introduce some systematics in the flux measurements. I don't have time to go over this in case you can ask. After we measure 3.6 and 4.5 color, we need to model them, and for this he assumed a very simple SED model made up of a featureless optical continuum whose slope can change, of course, and on top of which he added the emission line, H-alpha, sulfur, and I also guess nitrogen for H-alpha. And you can see here the result of doing this across a wide range of redshift from 2.5 up to redshift about 5. This is basically the 3.6 and 3.6 convolved with 4.5 transmission band. The equivalent width of H-alpha which are recovered are pretty high, about 500 angstrom, but these are consistent with measurements of H-alpha equivalent width from previous works at similar redshift and similar luminosity, so stellar mass. So from here, we can now convert the H-alpha luminosity into the number of ionizing photons, and so recover the ionizing efficiency. Here is this plot. He's showing a compilation of recent estimates of Xi-ion for luminosities basically brighter than -20, a redshift 4 to 5. And these are his new measurements. It's very nice because on average they are slightly higher. So fainter galaxies are slightly more efficient at producing ionizing photons than than brighter galaxies. This is great because fainter galaxies are more common, so they can help even more in the reionization. But we can also ask which escape fraction do this ionizing efficiency, does this ionizing efficiency imply? Well, if we plot the escape fraction as a function of Xi-ion using the UV luminosity functions, then it turns out that the required escape fraction are of the order of 3 to 7%, which is also great because we are well within recent constraint from Steidel, for example, at redshift 9. And actually, usually, we were thinking that so the need for escape fraction were between 10 and 20%. So this is, I think it's a very nice value. And finally, so of course, JWST will solve all our problems. But I would also like to say that if you have the power, in the meantime, between now and JWST launch, if you have the power, please extend the calls for observation for Spitzer, because it can still do quite a lot of very nice things. I'll leave here my conclusion, and thank you.
Questions?
Down to which UV luminosity did you integrate down the UV luminosity function to get the, the luminosity density?
I'm not 100% sure, but I think it's -13, which is not covered by observation right now, okay? But I think it's reasonable from models. I mean, the UV luminosity function shouldn't decrease by much, but again, I'm not 100% sure.
More questions? If not, let's thank again Stefano.
Thank you.